Tonight, we're going to do something a little different. We're not going to ask whether a generation ship could survive its journey or catalogue the many ways it might fail. Tonight, we're actually going to build one. Carefully, honestly, using real engineering studies that real scientists have already spent real careers designing. And then we're going to climb aboard together and simply ask, what would it actually feel like to live there? Here's what most people don't realize about this idea. It isn't science fiction dressed up as science. Somewhere in the world, right now, tonight, actual population geneticists are running actual computer simulations to determine exactly how many human beings a ship like this would need to carry to avoid slowly destroying its own gene pool over the centuries. Actual engineers, working with an actual international design competition, have already produced a detailed, physically grounded architecture for exactly this kind of vessel, complete with a name, a target population, and a very specific voyage length. An actual closed ecological system built at genuine, full human scale in the Arizona desert has already been sealed shut and has already taught us through real and sometimes painful failure exactly what it takes, and what it doesn't yet take, to keep a group of human beings alive without ever opening the door. The first surprise tonight is that a generation ship isn't really a choice, or a stylistic flourish borrowed from science fiction. It's the direct, unavoidable mathematical consequence of exactly how far away the nearest star actually is, and exactly how fast anything we could plausibly build could ever travel. The second surprise is that we already know, with real precision, exactly how large such a ship's population would need to be to remain genetically healthy across centuries, and that the number currently being used by the world's leading generation ship design competition sits well below what that same research recommends, a genuine, unresolved tension nobody in the field has yet settled. The third surprise is what it would actually feel like to live inside a spinning machine, generation after generation, where down isn't toward a planet at all, and where a tossed ball never quite falls the way your own body expects it to. And the fourth surprise, the one that reframes everything else, is a genuinely serious question some of the field's own researchers have raised, that a successful generation ship, once it finally arrives, might choose not to land at all. By the end of tonight, you're going to understand exactly what a real, physically grounded generation ship would need to be, how it would actually be built, what its passengers would actually experience across a voyage lasting longer than most nations have existed, and why so many of the questions it forces us to answer are already, quietly, being rehearsed right now in laboratories and design studios here on Earth. Before we dive in, if you're someone who finds real comfort in this kind of patient, honest exploration of the universe, who trades the noise of the day for a little cosmic perspective before sleep, consider liking this video or subscribing to the channel. It's a small thing, but it helps us keep making this kind of content for people who share that same quiet curiosity. Now, let's begin. Let's start with the specific, unforgiving arithmetic that makes a generation ship necessary in the first place. Because it's worth understanding that this idea isn't a preference. It's a mathematical conclusion, forced on us by the simple size of the universe we happen to live in. The nearest entire star system to our own, Alpha Centauri, sits approximately 4.37 light-years away. Its closest individual member, Proxima Centauri, sits slightly nearer still, at roughly 4.24 light-years, something in the neighborhood of 40 trillion kilometers, or 25 trillion miles. Voyager 1, humanity's fastest and most distant spacecraft, currently travels at approximately 17 kilometers per second, escaping our solar system at a rate of roughly 3.5 astronomical units every year. At that speed, reaching the distance of Proxima Centauri would take an estimated 73,000 years. A crewed mission faces an even steeper problem than an uncrewed probe like Voyager, because a ship carrying living passengers has to actually arrive. It has to decelerate, meaningfully, at the far end of its journey, rather than simply flying past its target forever. An uncrewed flyby probe never needs to slow down at all, which is exactly why serious flyby probe speed estimates, reaching 10 to 20% of light speed, run roughly double what's realistically achievable for a crewed vessel that also has to carry enough mass to shield, sustain, and eventually slow an entire living population. Even at a genuinely optimistic sustained cruise speed of 1% of the speed of light, a velocity considerably beyond anything ever actually built by any nation at any point in history. The one-way trip to Proxima Centauri would still take approximately 424 years. Scale that speed back to a more conservative, more closed ecology-friendly 0.5% of light speed, and the journey stretches to roughly 850 years. Here is the honest reason multi-century, multi-generational transit is close to unavoidable for any voyage undertaken with technology we can currently foresee. Every serious propulsion concept that doesn't require genuinely exotic, not yet invented physics, warp drives, traversable wormholes, and similar ideas that remain, for now, firmly in the realm of theoretical speculation, tops out well under 20% of light speed for an uncrewed probe, and considerably lower still for anything carrying enough mass to decelerate, shield, and sustain a living population across the entire distance. At any speed slow enough to actually be built with foreseeable technology, the total trip outlasts a single human lifetime. That gap between how far away the nearest star genuinely is and how fast we can plausibly travel is the entire reason the generation ship concept exists at all. It isn't a stylistic choice. It's the direct consequence of arithmetic nobody has yet found a way around. Here's a way to actually feel the scale of that arithmetic. A 250-year one-way voyage, the specific figure used by Project Hyperion, the most serious, currently active generation ship design study in the world today, which we'll spend considerable time with tonight, is longer than the entire history of the United States as a nation. A ship launched today, using that exact figure, would still be more than a century away from arrival by the time America itself reached its 350th anniversary. A crew member born partway through such a voyage would live an entire human life. Birth, childhood, work, old age, death, having only ever known the ship itself. Never Earth. And, depending on precisely where their own particular generation happened to fall within the full 250-year span, quite possibly never the destination either. Let's actually build this thing, using real engineering studies rather than pure imagination. Because the honest, genuinely remarkable truth is that serious scientists and engineers have already done a great deal of this work. The earliest serious attempt came from Project Orion, active between 1958 and 1965, which proposed an almost unbelievably blunt method of propulsion, detonating a continuous series of small nuclear bombs behind a heavily reinforced pusher plate, using the resulting shockwaves to physically push a spacecraft forward. In theory, the design was genuinely capable of reaching a meaningful fraction of the speed of light. In practice, it never flew, and remains, to this day, effectively barred by the 1963 Partial Test Ban Treaty, which prohibits nuclear detonations in space entirely. A considerably more refined and considerably more influential design followed between 1973 and 1978. Project Daedalus, a landmark study conducted by the British Interplanetary Society, led by engineers Alan Bond and Tony Martin, drawing on more than 10,000 combined work hours from roughly a dozen scientists and engineers. Daedalus was designed as an uncrewed, two-stage fusion pulse probe with a total launch mass of 54,000 tons. 50,000 tons of deuterium and helium-3 fusion fuel, and 500 tons of actual scientific payload. It targeted Barnard's star, roughly 5.9 light-years away, and was designed to cruise at a genuinely staggering 12% of the speed of light, arriving in approximately 50 years. It remains, even decades later, one of the most detailed, most carefully engineered interstellar propulsion concepts ever produced. A later effort, Project Icarus, ran from 2009 to 2019, undertaken by the organization Icarus Interstellar in partnership with the Tau Zero Foundation, specifically attempting to redesign and modernize the original Daedalus concept using contemporary scientific and engineering knowledge. It produced several genuinely interesting concept variants, including one called Icarus Firefly. But the project was quietly, unofficially wound down in 2019, without ever reaching a finalized replacement design. It's worth being honest about what that represents. Even the comparatively narrower task of updating a 50-year-old uncrewed probe concept using considerably more advanced modern engineering knowledge has proven genuinely difficult to actually complete. In 2011, a genuinely different kind of initiative began, the 100-year Starship program, jointly seeded by DARPA and NASA. Not a literal shipbuilding program at all, but a deliberate, coordinated effort to examine the organizational, technical, sociological, and ethical groundwork interstellar travel would eventually require. The program awarded a $500,000 grant to a non-profit consortium led by Mae Jemison, the first African-American woman to travel to space. One idea floated at the program's founding 2011 symposium, offered by Human Genome Project leader Craig Venter, proposed something genuinely radical. Skip sending living human beings across interstellar space at all, and instead transmit genetic and genomic data itself to potentially be reconstructed only once it actually arrived at its destination. It's worth being clear that this remains a speculative alternative, discussed seriously within the field, rather than any kind of mainstream mission architecture. But it's a real idea, raised by a genuinely credentialed scientist, worth including honestly. Physicist Gerard K. O'Neill, in 1976, contributed something slightly different but foundational to everything that followed, a detailed design for rotating space habitats, published in his book The High Frontier. It wasn't a Starship design in itself, but it became, and remains, the standard engineering reference for the actual living space any generation ship would eventually need, a topic we'll return to in real depth shortly. And the most detailed, most current real design study of all arrived recently, Project Hyperion and its winning concept, nicknamed Chrysalis, run by the Initiative for Interstellar Studies, an organization founded in 2011 by researcher Andreas Hein. Its 2024 to 2025 international design competition specified a target population of 1,000 people, plus or minus 500, undertaking a 250-year voyage. The winning Chrysalis concept has been described, in follow-up coverage, as scalable up to roughly 2,400 people, housed within a structure some secondary sources describe as approximately 58 kilometers, or 36 miles, long. Though it's worth noting honestly that this specific size figure comes from secondary reporting on the winning design, rather than the original competition brief itself. Every one of these serious studies agrees on one further, unglamorous but important detail. A real generation ship could never actually launch from Earth's own surface. It would need to be assembled entirely in orbit, or at a stable gravitational balance point called a Lagrange point, using raw material mined directly from the moon or from nearby asteroids, deliberately avoiding the enormous energy cost of lifting tens of thousands of tons of finished structure directly out of Earth's own gravity well. This echoes O'Neill's own original 1970s proposal, which likewise called for lunar and asteroid-sourced construction material, rather than material launched from Earth itself. Here's where the story moves from pure engineering into something considerably more human, and where we find one of the field's genuinely most contested, most unresolved open questions. In the 1980s, anthropologist John Moore of the University of Florida modeled a hypothetical generation ship population directly on the social structure of small hunter-gatherer clans, incorporating strong kin avoidance rules. Essentially, formalized incest taboos of the kind found in many real historical human societies, and concluded that a population of somewhere between 150 and 300 people could remain both socially and genetically sustainable across the generations of a long voyage. 3 decades later, anthropologist Cameron M. Smith of Portland State University revisited the exact same question using considerably more rigorous modern population genetics modeling. In a 2014 peer-reviewed paper published in the journal Acta Astronautica, titled "With Genuine Precision, Estimation of a Genetically Viable Population for Multi-Generational Interstellar Voyaging," Smith modeled a roughly 5-generation, 150-year voyage, carefully accounting for the accumulated effects of mutation, migration, selection, and genetic drift across that entire span. His conclusion arrived at a dramatically larger figure than Moore's earlier estimate, a properly age and sex-structured founding population of somewhere between roughly 14,000 and 44,000 people, a range often rounded, in subsequent discussion, to a simpler 10,000 to 40,000. Smith's modelling specifically found that a starting population of just 150 people, Moore's own original figure, would lose approximately 80% of its total genetic diversity within just 30 generations. Even a considerably larger starting population of 500 people, Smith's work found, remains genuinely too small a genetic base to sustain real, long-term, multi-generational health. A separate, independent 2017 computational study, a Monte Carlo simulation nicknamed Heritage, directly tested Smith's own parameters and modelling assumptions and confirmed his core finding: a founding population somewhere in the 14,000 person range is genuinely necessary for reliable multi-generational genetic health under the specific modelling framework Smith had proposed. Here is the genuine, unresolved tension worth naming directly, because it sits at the very centre of the entire field, right now, in real time. Project Hyperion, the actual, currently running, most serious generation ship design competition in the world today, sets its own official target population at just 1,000 people, plus or minus 500. That figure sits well below Smith's own recommended safe range, despite Smith himself being a genuinely respected, professionally involved figure within the broader interstellar studies community these design competitions actually emerge from. Recent commentary on this specific gap, published in 2025, has explicitly questioned why generation ship design teams aren't more consistently required to include dedicated population genetics expertise, given how significant this discrepancy actually is. This isn't a settled disagreement, quietly resolved somewhere in the background of the field. It remains alive, openly acknowledged tension, sitting directly at the heart of the most serious ongoing generation ship design effort currently underway anywhere. For genuine comparison, real habitat capacity designs, built for entirely different purposes than interstellar travel, cluster consistently toward the higher end of this range. O'Neill's own Island 1 concept was explicitly sized for 10,000 people. The British Interplanetary Society's separate Avalon concept targeted the same figure, and the 1975 NASA-sponsored Stanford Taurus summer study, involving both O'Neill himself and future rocket engineer Eric Drexler, was designed around a population of 10,000 to 14,000. Modern proposed mitigations for this genetic bottleneck problem do exist, at least on paper: frozen banks of sperm, eggs, and embryos, intended to supplement genetic diversity without requiring the larger living population Smith's modelling actually calls for, and advanced gene editing technology intended to actively correct emerging genetic bottlenecks as they arise across the generations. It's worth being honest that neither of these represents a proven, currently deployable technology. Both remain genuinely speculative future solutions to a problem the field itself has not yet fully resolved. Here's a detail worth sitting with directly, because it reframes the entire scale of this problem. The genetic bottleneck range Smith calculated, 14,000 to 44,000 people, sits, strikingly, in roughly the same order of magnitude some researchers estimate for humanity's own ancient population bottleneck, tens of thousands of years in our own deep evolutionary past, which means a generation ship's worst-case starting population would be deliberately, knowingly recreating a scale of genetic risk our own species has already, entirely by accident, managed to survive once before. Before we walk the crew through the actual voyage itself, it's worth pausing on a genuinely important question. Why would anyone, ever, actually choose to do this? The serious interstellar studies literature, drawing on Icarus Interstellar, the 100-year Starship program, and the Initiative for Interstellar Studies alike, consistently returns to a small, recurring cluster of motivating reasons. Species-level backup against genuine existential risks, a large asteroid impact, a supervolcanic eruption, an engineered pandemic, or some form of self-inflicted global catastrophe, any of which could threaten humanity's entire existence if we remain confined to a single planet indefinitely. Long-term resource and habitat pressure, treated as a rationale for eventually expanding meaningfully beyond one single world. And, cited explicitly and directly by the organizers of the 100-year Starship program themselves, simply the basic, deeply rooted human exploratory drive. Treated as a legitimate motivator in its own right, standing alongside the more purely practical justifications. The 100-year Starship program was explicit from its very founding that its actual purpose was never to build a literal ship at all. It existed instead to seed the organizational and economic groundwork, sustainable funding models, genuinely cross-disciplinary research pipelines, and multi-decade institutional commitment. Treating those specific, unglamorous foundations as the real bottleneck standing in the way of interstellar travel rather than propulsion physics itself. This is a real, explicitly stated framing from the program's own organizers, not simply an outside inference about their goals. Most serious studies agree on a small handful of milestone technologies that would genuinely need to mature considerably further before any of this becomes physically realistic. Genuinely closed-loop life support, which, as we're about to see in real detail, has not yet been achieved at any meaningful scale. Practical, radiation-tolerant rotating habitat construction at the multi-kilometer scale, which has never actually been built. And orbital or lunar and asteroid-based heavy manufacturing capability, which does not currently exist in any form. It's worth being genuinely honest about one further point. Whether humanity ever actually commits the staggering resources such a project would require is fundamentally a political and economic question with no scientific answer available. Serious engineering studies model the feasibility of such a mission. Whether it could, in principle, actually be built and successfully undertaken. They are, quite deliberately, considerably more careful about ever predicting the likelihood that humanity will actually choose to attempt it. Now let's actually depart and walk through the true, honest scale of simply leaving our own solar system, because this is where most casual conversations about interstellar travel genuinely underestimate what the journey actually involves. The heliopause, the boundary where our sun's own outward-flowing solar wind finally gives way entirely to true interstellar space, sits at roughly 123 astronomical units from the Sun, somewhere between 18 and 19 billion kilometers out. Voyager 1 crossed that specific boundary in August 2012, a full 35 years after its original 1977 launch. The Kuiper Belt, a broad ring of icy debris left over from the solar system's own formation, extends roughly 30 to 50 astronomical units from the Sun, with more recent 2024 data hinting the true boundary may actually extend as much as 20% farther out than previously modelled. And the Oort cloud, our Sun's true, outermost gravitational edge, the actual boundary of its own domain, is estimated, with genuine, openly acknowledged uncertainty, even within NASA's own published materials, to begin somewhere around 1,000 to 5,000 astronomical units from the Sun, and extend outward to somewhere in the neighbourhood of 100,000 astronomical units, roughly 1.6 light-years at its very outer boundary. Here's the detail worth sitting with directly, because it reshapes the entire shape of the voyage we're describing tonight. A ship bound for another star doesn't simply leave the solar system once, in a single, clean, dramatic moment, the way a spacecraft leaving a planet's atmosphere does. It spends a genuinely enormous fraction of its total journey, potentially well over a full light year, out of the roughly 4.2 light-year total distance to Proxima Centauri. Still technically inside the Sun's own gravitational domain, moving slowly through the sparse, city-sized iceberg-strewn outer edge of it, long before anything resembling true interstellar space actually begins. Every serious propulsion study, Daedalus included, uses a carefully staged acceleration profile rather than continuous thrust for the entire voyage. Daedalus's own design called for roughly 2 years of active first-stage acceleration, followed by approximately 1.8 more years of second-stage acceleration, and then decades of entirely unpowered coasting. Because carrying enough fuel to both accelerate and later decelerate across the entire distance roughly squares the already brutal fuel mass problem involved. A crewed generation ship, needing to genuinely decelerate upon arrival rather than simply flying past its destination, faces this doubled fuel penalty in its full, unavoidable severity, which is precisely why realistic crewed mission cruise speeds sit so much lower than the more optimistic, uncrewed probe benchmarks set by designs like Daedalus. Here's a way to actually feel the true proportions of this journey. If a generation ship's entire roughly 250-year voyage were compressed down into a single 24-hour day, the ship would spend its entire morning, from midnight all the way to nearly noon, simply crossing the outer, thinly populated edge of its own home star's gravitational domain without having yet entered true interstellar space at all. Half of an entire compressed day spent leaving home. Once genuinely underway, the ship's passengers would face an immediate, permanent, physical problem that has nothing to do with propulsion at all. How do you keep an entire multi-generational population healthy for centuries with no planet beneath their feet to provide gravity at all? The answer, according to essentially every serious study, comes down to rotation, rather than any exotic gravity-generating technology. The underlying physics is genuinely simple. Centripetal acceleration, governed by the equation A equals r times omega squared. Acceleration equals radius, multiplied by angular velocity squared. Spin a large enough structure fast enough, and anyone standing on its inner surface experiences an effective outward force, functionally indistinguishable from ordinary planetary gravity. The classic O'Neill cylinder design calls for 2 counter-rotating cylinders, spinning in opposite directions specifically to cancel out unwanted gyroscopic drift that a single rotating structure would otherwise develop. Each one roughly 6.4 to 8 kilometers in diameter, with a radius of roughly 3.2 to 4 kilometers, and approximately 32 kilometers long, spinning at somewhere between half a rotation and 1 full rotation per minute to produce a comfortable, Earth-like 1g of effective gravity along its inner surface. There's a genuine, unavoidable engineering trade-off built directly into this design, worth understanding in real detail. Smaller, considerably cheaper, considerably easier to build habitats need to spin proportionally faster to achieve that same 1g of gravity. But faster rotation, at a smaller radius, produces noticeably stronger Coriolis effects. An object dropped near the habitat's floor would appear to visibly curve sideways rather than falling in a perfectly straight line, and rapid head movements, particularly turning quickly, can genuinely induce dizziness or nausea in the people living there. A widely cited engineering rule of thumb holds that rotation faster than roughly 2 revolutions per minute begins becoming perceptibly, genuinely disorienting for most people, which sets a practical minimum radius of roughly 224 to 225 meters to achieve full 1g gravity without introducing excessive Coriolis discomfort into daily life. Below that specific radius, designers are forced to either accept a lower overall spin gravity level or accept a real, ongoing measure of crew discomfort as the cost of a more compact, more buildable structure. It's worth understanding directly why rotational gravity is treated as essentially non-negotiable, rather than simply a nice-to-have design feature across nearly every serious generation ship study. NASA's own extensive long-duration astronaut research has documented, in real physiological detail, measurable bone density loss, muscle atrophy, cardiovascular deconditioning, and vision changes, all beginning within mere weeks of sustained microgravity exposure aboard the International Space Station. For a mission measured not in weeks or months, but in genuine centuries, sustained zero or partial gravity isn't a minor inconvenience to be managed. It would very likely be physiologically catastrophic, compounding across generation after generation who have never once experienced anything else, which is precisely why essentially every serious generation ship design treats rotational artificial gravity as a foundational, non-negotiable requirement rather than an optional engineering nicety. Beyond the classic O'Neill cylinder itself, real historical designs have explored genuine alternatives. The Stanford Torus, from that same 1975 NASA summer study, envisioned as a single ring roughly 1.8 kilometers in diameter, sized for a population of 10,000 to 14,000 people. And, more recently, a design called Kalpana 1, a considerably smaller radius torus specifically intended to solve the practical problem of needing several kilometers of radius to comfortably spin at 1G, using a more modest, more buildable overall structure instead. Picture what daily life inside such a structure would genuinely feel like. Inside a rotating habitat, down isn't toward any planet at all. It's outward, away from the ship's own central rotational axis. Walk deliberately toward that central axis, and you would feel yourself growing progressively, measurably lighter with every step. Reach the exact dead center of the structure, and you would simply float, entirely weightless, regardless of how heavy the outer rim of the same habitat feels at that very moment. Toss a ball straight upward, and it would not fall straight back down into your waiting hand. It would visibly, permanently curve to one side. A small, constant, physically built-in reminder for every single human being ever born aboard, across every single generation of the entire voyage, that the world they call home is a spinning machine, not a planet. Now we arrive at the single hardest, most genuinely unresolved engineering problem any generation ship would actually have to solve: keeping its entire population alive, breathing, fed, and hydrated indefinitely, with absolutely nothing coming in from outside and absolutely nothing going out. We don't have to speculate about how difficult this actually is, because humanity has already run the experiment at real, full human scale and watched it genuinely struggle. Biosphere 2, located in Oracle, Arizona, sealed 8 crew members, who came to be known as the Biospherians. Inside a genuinely enormous, roughly 3-acre glass and steel structure, costing approximately $150 million to construct, containing 5 distinct engineered biomes: a rainforest, an ocean and coral reef, a mangrove wetland, a savanna, and a desert, alongside dedicated agricultural space from September 1991 to September 1993. The core failure, and the one worth understanding in genuine physical detail, was a steady, alarming decline in atmospheric oxygen. Over the first 16 months of the sealed experiment, oxygen levels fell steadily from a healthy, normal 20.9% down to roughly 14%. An atmospheric oxygen level equivalent to what you'd experience at somewhere between 13,000 and 15,000 feet of elevation, genuinely sufficient to cause real, measurable fatigue, cognitive impairment, and disrupted sleep among the crew living inside. The specific, entirely unanticipated cause turned out to be genuinely fascinating and genuinely humbling. The enclosure's own soil contained considerably more organic matter than the project's designers had originally planned for, and soil-dwelling microbes were consuming oxygen while decomposing that excess organic material far faster than the enclosed plants could actually replace it through photosynthesis. The resulting excess carbon dioxide then reacted directly with the facility's own structural concrete, forming calcium carbonate and effectively locking that gas permanently out of circulation. An unanticipated chemical interaction nobody had modelled in advance. Outside oxygen eventually had to be deliberately pumped in from beyond the sealed structure, breaking the entire closed premise the experiment had been specifically designed to test. The secondary failures compound the picture further. Significant crop shortfalls and genuine weight loss among the crew members themselves. Real ecological imbalance, with roughly 30% of the enclosure's originally introduced species eventually dying out entirely, the facility's pollinating insects collapsing completely, and opportunistic ants and cockroaches becoming dominant in the resulting ecological vacuum, and genuinely documented interpersonal conflict among the crew themselves. Though it's worth including, honestly, that later insider accounts, including biospherian Mark Nelson's own book Pushing Our Limits, have argued that press coverage at the time significantly oversimplified the project's failure narrative, and that Biosphere 2 generated genuinely valuable, lasting scientific insight regardless of how dramatically its early struggles were reported. Here's the detail that connects this experiment directly back to tonight's central subject. Biosphere 2's own original planners explicitly framed the entire project around the question of eventual space colonization. One contemporary account from the project directly quotes its organizers asking readers to imagine, quite specifically, building a large ship that will travel through space as the project's own underlying motivation from the very beginning. The field's response since Biosphere 2's own difficult lessons has moved deliberately away from attempting another all-at-once, full-scale closed system and toward a considerably more incremental, more carefully staged approach. The European Space Agency's ongoing MELASESA program, initiated in 1989, and now involving roughly 30 partner organizations as of 2023, tests closed-loop life support incrementally rather than all at once. MELASESA's pilot facility in Barcelona currently works towards sustaining a colony of laboratory rats indefinitely, using a carefully engineered bioreactor-based loop, modelled directly on the natural function of a lake ecosystem using algae and bacteria, designed to convert organic waste and carbon dioxide directly into breathable oxygen, drinkable water, and edible food, deliberately proving the underlying concept at a smaller, more manageable scale before ever attempting anything resembling a genuine human-scale closed system. The raw resource numbers involved are worth stating plainly, because every single unit eventually has to be recovered and recycled, never simply resupplied, aboard a real generation ship. Roughly 3.56 kilograms of drinking water per person, per day, plus an additional 26 kilograms of hygiene water per person, per day, every single litre of which would need to be captured, purified, and returned to circulation indefinitely for the entire multi-century duration of the voyage. It's genuinely important to state plainly, in the interest of complete honesty. No closed ecological system, at any scale, anywhere, has yet been demonstrated to sustain a human population indefinitely, without any external input of any kind. This remains, without serious competition, the single largest unresolved engineering gap standing between our current technology and an actual, functioning generation ship. Beyond the protective shelter of Earth's own magnetic field and atmosphere, a generation ship would face a continuous, unrelenting bombardment of galactic cosmic rays, composed of roughly 90% high-energy protons, 9% alpha particles, and a smaller remainder of heavier atomic nuclei, arriving from every direction simultaneously at energies ranging from the hundreds of millions of electron volts up into the billions, alongside periodic, more intense bursts called solar particle events. The shielding math involved is, honestly, genuinely brutal. Comprehensive cosmic ray shielding, sufficient to meaningfully protect a living population across an entire multi-century voyage, is estimated to require something on the order of a 5-meter thick shell of water, or an equivalent mass of some other suitable shielding material surrounding every habitable section of the ship. Even a considerably more modest 1-meter water shell is described directly in the technical literature as excessively heavy for any real buildable mission, because the required shielding mass compounds directly with every other design constraint the ship already faces. More shielding mass demands more fuel to move it, which demands more total mass to shield in turn in a genuinely difficult, self-reinforcing engineering spiral. For reference, NASA's own standard for career radiation exposure among astronauts is sometimes cited at around 400 rem, or 4 sieverts, a threshold associated with meaningfully elevated lifetime cancer risk. Separate NASA technical studies, focused specifically on shielding requirements for low Earth orbit class missions, calculate that roughly 17.5 grams per square centimeter of aluminum shielding would be required to keep annual radiation dose under a 50 centisievert limit. It's worth being honest that these specific figures are drawn from interplanetary and low Earth orbit mission studies, rather than any dedicated generation ship-specific research. They represent the closest real, quantitative anchor currently available, rather than a figure calculated specifically for a centuries-long interstellar voyage. There's a genuinely important complication buried inside this entire problem, worth understanding directly. According to researchers who specifically study radiation shielding for extended space missions, simply doubling a hull's total thickness reduces overall radiation exposure by only around 10%, because the very highest energy cosmic rays simply pass straight through most practical shielding material regardless of how thick it becomes. Brute force mass shielding, in other words, has genuine, hard physical limits. Some researchers in this field have specifically argued that reducing total time spent in transit matters considerably more than increasing shielding thickness ever could, a solution that is, by definition, structurally unavailable to any generation ship, whose entire defining feature is a transit time measured in centuries rather than months. This represents a genuine, acknowledged tension sitting directly at the heart of the entire generation ship concept. Its unavoidably long transit time is precisely the variable radiation science says matters most, and precisely the one variable it fundamentally cannot reduce. Alternative, considerably less mass-heavy approaches remain under genuine active research, though none has yet been flight-proven at any meaningful scale. Active magnetic field deflection systems, using large superconducting coils to actively deflect incoming charged particles, mimicking the same basic principle behind Earth's own natural magnetosphere, rather than simply absorbing incoming radiation through sheer physical mass. And beyond the population genetics questions we already walked through earlier tonight, sustained low-level radiation exposure accumulating across every single generation aboard for centuries raises genuinely serious, still actively researched questions about cumulative mutation rates over that same extended span. It's worth being fully honest that, according to the sources available for this exact question, dedicated multi-generational human radiation data simply does not currently exist at any real scale, anywhere. This remains a genuine, acknowledged open research gap, not a problem anyone currently claims to have solved. Now, let's turn to something that has no clean engineering solution at all, because it isn't really an engineering problem in the first place. What happens to human society itself, sealed inside a single ship, with no possibility of contact with anyone outside it, for the equivalent of 10 or more consecutive human generations? The single closest real experimental precedent for this specific kind of extended isolation comes from Mars 500, an experiment conducted in Moscow, run by Russia's Institute for Biomedical Problems in cooperation with the European Space Agency. 6 crew members were sealed inside a mock spacecraft for 520 consecutive days, from 2010 to 2011, specifically to study the psychological effects of prolonged isolation. It remains the longest such controlled human confinement study ever conducted, and it is still, honestly, 3 full orders of magnitude shorter than what a real multi-generational voyage would actually require. Beyond formal scientific experiments, a handful of genuine historical analogues offer at least partial, imperfect precedent. Multi-month age-of-sail naval and whaling voyages provide a real, if considerably shorter, precedent for closed crew social dynamics and command structure under sustained isolation, though measured in months, never in generations. And genuinely multi-generational historical migrations and isolated settlement patterns, long-distance Pacific voyaging societies, and various historically isolated island or Arctic communities offer some meaningful precedent for cultural continuity and identity persistence across multiple generations without meaningful outside contact, though none of these historical examples combine that same extended timescale with the kind of total, absolute physical enclosure a genuine generation ship would represent. There remains a genuinely open legal and political question here, worth stating with real honesty. No existing international framework, including the 1967 Outer Space Treaty, which governs the conduct of nations in space but was never written with a multi-generational, entirely self-governing population born completely off any celestial body in mind, clearly addresses what citizenship, legal jurisdiction, or political status a population born and raised entirely aboard such a ship would actually hold, either during the voyage itself or upon eventual arrival at a destination system with no pre-existing legal authority of any kind waiting to receive them. And there's a specific, genuinely uncomfortable ethical tension, actively, explicitly discussed in recent commentary surrounding the real Project Hyperion design competition. Every single generation after the founding crew would be born directly into this mission without ever having personally chosen it at all. This remains a documented, seriously discussed ethical concern within the field itself, without any settled resolution currently on offer. Let's spend a moment on the ship's own internal governance, not its human governance, but its machine governance, because every serious design study treats this as a genuinely central problem in its own right. Every serious design study assumes extensive automation, handling navigation, continuous life support monitoring, and structural maintenance, simply because a mission measured in centuries cannot realistically depend on any single generation's own skill level or attentiveness remaining perfectly, reliably constant across the entire span of the voyage. Automated systems, properly designed, provide a kind of continuity, a constantly changing human population, generation after generation, simply cannot guarantee entirely on its own. There are specific areas, though, where serious proposals consistently, deliberately insist on keeping actual human beings directly in the decision-making loop, rather than fully automating the process. Genuinely life or death resource allocation decisions, reproduction and population management, and overall governance itself. Areas where the underlying ethical and social stakes are consistently treated as inappropriate to delegate entirely to automated systems, even in cases where the raw technical capability to do so might genuinely exist. On the specific question of manufacturing, because a centuries-long mission simply cannot practically carry a spare parts inventory sufficient for every conceivable eventual failure, most serious design studies. Icarus Interstellar's own published literature included, assume the ship must carry genuine onboard manufacturing capability of its own, effectively, a fully self-contained industrial base, capable of fabricating entirely new replacement components from raw or recycled material throughout the voyage's full duration, rather than relying on any fixed launch day inventory of pre-manufactured spare parts. It's worth being honest that the specific, precise balance between artificial intelligence autonomy and direct human control for a real, functioning multi-century mission remains genuinely speculative, reasoned from general automation and reliability engineering principles that already exist, rather than drawn from any dedicated, published generation ship-specific artificial intelligence architecture study currently available. No human-built machine has ever been required to function continuously, entirely unattended by its own original builders, for anything genuinely close to the multi-century timescales a real generation ship would demand. the longest continuously operating spacecraft systems humanity has ever actually built. The twin Voyager probes, launched back in 1977, have managed under 50 years of continuous operation, and even they have had to progressively shut down individual instruments, one at a time, simply to conserve their own steadily decaying radioisotope power supply. The resulting design philosophy, widely shared across essentially every serious generation ship study currently in existence, rests on three consistent pillars. Radical simplicity, deliberately minimizing the total number of individual potential failure points wherever genuinely possible. Deep redundancy, providing multiple, fully independent backup systems for every single critical function aboard the ship. And genuine onboard manufacturing and repair capability, rather than relying on any single component's ability to simply last the entire voyage, unmaintained and unreplaced, from launch all the way through to final arrival. There's a further, genuinely important dimension to this problem worth including directly. Knowledge continuity itself is treated, throughout this serious literature, as a genuine engineering problem in its own right. Not merely a cultural nicety to be handled informally. Specific, dedicated discussions in this field note that technical skills and detailed system knowledge must be actively, redundantly taught and consistently reinforced across every single successive generation, because a multi-century mission that ever loses the institutional knowledge of how its own core systems actually function becomes genuinely unrecoverable in a way a considerably shorter mission would simply never risk in the first place. It's worth being honest that this remains a widely discussed, genuinely serious concern throughout the literature, rather than any kind of proven, solved design problem. No generation ship study currently claims to have a fully proven, guaranteed method for ensuring multi-century knowledge transfer actually succeeds. Here is where tonight's story takes its most genuinely surprising turn, arriving at a real, seriously considered idea that upends the entire premise most people naturally assume a generation ship is actually working toward. The ship's eventual deceleration phase mirrors its earlier acceleration phase in reverse, and because a crewed vessel must genuinely slow itself down, rather than simply continuing past its intended destination indefinitely, this final phase consumes a comparably enormous share of the mission's total fuel mass. A major reason, once again, why realistic crewed generation ship cruise speeds sit so dramatically below uncrewed benchmarks like Daedalus's own theoretical 12% of light speed. But here is the genuinely serious argument, discussed directly within real interstellar studies literature, worth sitting with carefully. A successful generation ship might, quite deliberately, choose not to land at all. The underlying reasoning runs like this. A multi-generational population, born and fully adapted entirely to life within an artificial, rotating habitat, with its own internal ecology, its own artificial gravity, its own entirely self-contained culture already thoroughly solved, refined and stabilized across centuries of continuous operation, may genuinely find continuing to live inside more of exactly these same kinds of habitats, potentially newly constructed from the destination system's own available asteroid or moon resources, a considerably lower risk, more genuinely familiar choice than committing an entire population to an unproven planetary surface, with its own unknown biochemistry, unfamiliar gravity, and unfamiliar atmosphere. It's worth being clear that this remains a real, seriously discussed position within the field, rather than this documentary's own speculation. Though it also remains, honestly, a minority, genuinely contested view within that same field, rather than any kind of settled consensus. And even for a generation that does eventually choose to land, there's a genuine, entirely unresolved disorientation problem worth including directly. Every single crew member born aboard the ship would have spent their entire life beneath a spinning habitat's own outward-pointing artificial gravity, beneath a visibly curved horizon under an entirely artificial sky. how such a population would actually, physically and psychologically, adapt to a genuine planetary surface. Real, fixed direction gravity, real unpredictable weather, an actual, permanently straight horizon they have never once directly experienced in their entire lives, remains a genuinely open question in the literature, without any confident, settled answer currently on offer. Before we close, let's gather everything we've walked through tonight and sit with what it would genuinely, actually feel like to live this entire story from the inside. A person born partway through a real 250-year generation ship voyage, using Project Hyperion's own actual, currently proposed mission parameters, would live an entire complete human life. Birth, childhood, work, old age, and eventually death, having never once, at any point, experienced an actual planet. Never unfiltered sunlight, arriving directly from an unobstructed sun. Never genuine, unpredictable weather. Never a horizon that wasn't the gently curving inner wall of a slowly rotating cylinder. Across a roughly 250-year voyage, assuming something in the neighborhood of 3 full generations per century, a single ship might carry somewhere between 7 and 10 complete human generations from departure all the way through to eventual arrival, meaning the ship's founding crew and its eventual arriving crew would be as distantly related to one another in genuinely lived experience and shared cultural memory as any person alive today is from ancestors who lived centuries before their own nation was even founded. Every single element we've walked through tonight, the raw physics of the crossing itself, the genuinely contested population genetics mathematics, the failed and carefully reattempted closed ecosystems, the hard physical limits of radiation shielding, the entirely unanswered legal status of a people born on no planet at all, describes, from a series of different angles, the exact same underlying human situation. A group of people choosing to build an entire, complete, fully self-contained world, small enough to actually construct and light enough to actually move, and then trusting that world and trusting each other across a span of time considerably longer than most nations in human history have ever managed to survive. There's something genuinely worth sitting with here, now that we've walked through the entire voyage together, from departure all the way to an uncertain, possibly permanently deferred arrival. There is no single part of this entire project that isn't already, quietly, being rehearsed in miniature, right now, tonight, somewhere here on Earth. Inside a sealed bioreactor in Barcelona, patiently teaching bacteria and algae how to sustain a small colony of laboratory rats indefinitely, one careful incremental step at a time. Inside population genetics, spreadsheets, modelling 30 full generations of a crew that has not yet been born and may never be. Inside a real, currently open design competition, asking ordinary working engineers and architects to seriously design a functioning, stable, multi-century society for people who do not yet exist. The ship itself, if it is ever actually built, will genuinely be something new under the sun. The largest, most ambitious single construction project our species will likely have ever attempted. But the deepest questions it forces humanity to actually answer before it could ever be built at all are not new questions in any meaningful sense. They are the same questions any small, genuinely isolated human community has always eventually had to answer throughout the entirety of our shared history about how to live well together, how to fairly share limited resources, how to raise children who never chose the circumstances of their own birth, and how to remain a genuine, functioning society across generations. Tonight's story simply asks those same old, familiar human questions at a scale, and across a duration, absolutely nothing in our history has ever fully tested before. Picture it, one final time before we close tonight. A ship departs. Not tomorrow, not soon, but someday, once enough of tonight's genuine engineering gaps have finally, patiently been closed. It carries, aboard it, somewhere between 1,000 and 40,000 people, depending on which serious study's own careful mathematics eventually wins the argument. For the first quarter of a compressed single day, it does nothing more dramatic than slowly cross the thin, icy, sparsely populated outskirts of its own home star's gravity. Still, technically, still at home for all those long, patient hours. Aboard it, a spinning, cylindrical world, its own artificial gravity pointing permanently outward rather than downward, its horizon gently curving upward at both ends rather than stretching flat and level to the sky. Forests, grown entirely under artificial light. Water, endlessly, patiently recycled through pipes engineered to lose less than the barest possible fraction of 1% with every single cycle. A magnetic shield, quietly humming, deflecting a ceaseless rain of cosmic particles that would otherwise, slowly, damage everything and everyone living inside. The first generation departs knowing, with total and complete clarity, exactly what they are personally choosing to give up forever. The second generation is born already aboard, inheriting a mission they never once personally agreed to, in a world that has no genuine outside left in it at all. By the fifth, or the seventh, or the 10th generation, the green, blue, distant planet their earliest ancestors once actually stood on has become something considerably closer to an old, half-remembered myth. A bedtime story told to children who have never once felt real, unfiltered wind, real rain, real direct sunlight on entirely unprotected skin. And if everything holds, if the oxygen never quietly vanishes into the walls the way it once nearly did in a glass structure in the Arizona desert, if the shielding genuinely holds against a ceaseless rain of radiation for 2.5 centuries running, if the population somehow remains large enough and diverse enough to survive whatever disease eventually, inevitably finds it, if the ship's own internal governance somehow holds together longer than any single human government in the entirety of recorded history, then, eventually, centuries after the very first generation ever stepped aboard, one final generation looks out through a window that has genuinely never shown them anything but stars and seas, for the very first time in the ship's entire multi-century existence. One particular point of light growing steadily, unmistakably larger. They may choose to land. They may, just as genuinely, choose not to. Content, after centuries of practice, inside the only kind of world they have ever actually known. Either way, they will have arrived, having never once known Earth at all. Tonight, we didn't ask whether a generation ship could survive its own journey. We built one, together, using real, carefully documented engineering studies, and then asked, honestly, what it would actually feel like to live aboard it. We found that the entire concept isn't a stylistic choice at all, but the direct, unavoidable mathematical consequence of exactly how far away the nearest star genuinely is, set against exactly how fast anything we can currently foresee building could ever travel. We found real, already completed engineering studies, Project Daedalus, Project Hyperion, and its winning Chrysalis concept, and Gerard O'Neill's own foundational rotating habitat designs, providing a genuine, physically grounded architecture for exactly this kind of vessel. We found a real, currently unresolved scientific tension at the very heart of the field. Population geneticists recommending tens of thousands of founding passengers for lasting genetic health, set directly against a real, currently active design competition working from a target of just 1,000. We found an entire morning, compressed from a 250-year voyage into a single day, spent simply leaving our own solar system's own outer, icy edge. We found a spinning artificial world, where gravity points outward rather than down, and a tossed ball never quite falls the way any of us have ever instinctively expected it to. We found a real, full-scale closed ecosystem sealed shut in the Arizona desert that nearly suffocated its own crew through a chemistry nobody had ever thought to model in advance. And the considerably more careful, more incremental research that followed directly from that difficult, honest lesson. And we found, at the very end of the entire voyage, a genuinely serious argument that a successful ship, having spent centuries perfecting an entirely self-contained way of life, might ultimately choose never to land at all. None of this is a story about certainty or about a project already fully solved and simply waiting to be built. It's a story about exactly what it would take, and exactly what it would feel like for a group of human beings to choose to become an entire, self-contained world, and about the fact that every single piece of that eventual choice is already, quietly, patiently being rehearsed right now, here on the one world we currently have. Sleep well tonight on a planet that has already been sustaining an entire, wildly complex, fully closed ecological loop for you without your ever needing to notice it working for the whole of your own life. Good night, and rest well under the stars, and under the quiet, patient, ongoing work of everyone still trying to learn exactly what it would take to one day build a world small enough to carry us there.